Good morning all. So today we are going to discuss about ohmic heating. So in this lecture we are going to discuss about the basics of ohmic heating and what are all the lab and lab scale and pilot scale systems available for ohmic heating, and what are all the critical parameters one needs to consider while applying ohmic heating for thermal processing of food. Actually, in first 10 classes we have discussed enormously about the thermal processing, conventional thermal processing applied for the food materials. Then last class we have also discussed about the microwave as well as the radio frequency heating, so which is nothing but a novel processing technologies. And today we are going to discuss about the ohmic heating principle. So if we see conventional heating, the major heat transfer mechanisms are conduction, convection and radiation. So the conduction mainly applied to solid food, convection mostly liquid food, and sometimes we may also get liquid and particulate solids. Right. The radiation comes when the heating medium is used as a hot gases or sometimes microwave. Right. So both steady as well as unsteady operation. Steady is nothing but a time independent, unsteady operation is dependent on time. Employing electrical energy directly into the food processing have attracted interest in the food industry in recent decades. So instead of using the temperature, so how do we do the food processing? By employing directly the electrical energy. That is the way the ohmic heating concepts came up. So this is especially useful when particulate food particles are there on a commercial scale, provides the food processor with the opportunity to produce new and value added food products with enhanced quality attributes. So this is very much important, since we are not applying the temperature directly, high temperature directly. So our quality attributes are much more higher than compared to any other conventional thermal processing, right. And also it is useful when the food particle contains the particulate matters, so which is difficult in the conventional thermal processing techniques, because if you remember, we have also told in the certain heat exchangers there is a limitation on how much the size of the particulate solids should be while processing. So these kind of restrictions can be relaxed in terms of ohmic heating. So it is especially designed to handle the food which has particulate solids, and also it is proven commercially to enhance the quality attributes of the food materials. Ohmic heating is an electroheating technique based on the passage of electrical current through a food product having electrical resistance. So it works under the principle of Ohm's law, so which you might have studied in your school science. So you may be familiar with, which is nothing but V equal to IR. So V is nothing but a voltage, right, in volts, and your I is nothing but a current in amperes, and R is nothing but a electrical resistance. Okay. So the current flowing through the liquid food is nothing but V upon R, voltage applied across the electrodes, and the resistance, electrical resistance or electrical conductivity of the food material. Heat is generated instantly inside the food, and its amount is directly related to the voltage gradient and the electrical conductivity. That is what I told, voltage gradient applied and electrical resistance 1 upon R is nothing but a electrical conductivity. So what are all the advantages? One is the lack of high wall temperature. So how do we do normal conventional process, conventional thermal processing? So if you have a solid food particle, you are supposed to apply a heat. So this has to penetrate through the solids. It is based on the thermal conductivity. If it is a liquid, it is a purely of convection phenomena. So everywhere the heat has to penetrate through the walls of the container, right. So, that is avoided here because your electrical energy is directly applied to the food material, liquid food products, and limiting heat transfer coefficient requirements. So, we have also seen in our earlier lectures. So, if it is a solid conduction, it is mainly based on the thermal conductivity of the food material. So, this thermal conductivity is only based on the material, the food material what we use, right. So, here it depends upon the heat transfer coefficient. So, one thing we should remember here is this heat transfer coefficient, it is not only the property of the food particle, the orientation of the container and the velocity of the food material which is passing through the processing system. So, everything is into account, it is a function of many factors, right. So, in this case of ohmic heating, so I do not have that the limiting or constraint of heat transfer coefficient. And maintaining the color and nutritional value of the food, as I told already. So, the ohmic heating is the main requirement or the main aim of going for ohmic heating is for two main aspects. One is for quality attributes. Since we are not applying the high temperature, the color and nutritional value of the food can be maintained, and shorter processing time obviously, because we are directly employing the electrical energy to heat the food, and higher yield compared to conventional thermal technologies, and rapid heat generation because it is also a volumetric heating phenomena, because you are not doing it via surface what you do in conventional thermal processing techniques, and it is a volumetric heat generation. So, that is why rapid heat generation would be there, and temperature increase is uniform due to volumetric heating principle, and reduces the thermal damage and nutritional losses. So, that is related to here maintaining the nutritional value of food, and acceptable textural property, minimum aroma loss, and high sensory quality. So, this is also one of the main advantage when we use ohmic heating. The application wise, ohmic heating is used for preheating, blanching, pasteurization, sterilization, and extraction of food products in almost all main thermal processing of food it is employed. Approved by USDA and FDA and used commercially for pumpable fluids. So, which is nothing but a inline, right. It is used for pumpable fluids which contains syrups including whole fruits, fruit juices, whole fruits in the sense pulps are high. We have already seen it is mainly employed for the food material which has large food chunks, right, and fruit juices, egg, milk, etc. So, all pumpable fluids it is used. The commercial technology is developed in USA, Japan, UK and other several European countries for the pasteurization as well as the aseptic packaging. The ohmic heating is a thermal electrical method where food is in contact with the electrodes, also known as joule heating, electroconductive heating, electrical resistance heating, direct electrical resistance heating and electro heating. So, all names same ohmic heating. So, remember here there are two electrodes. So, the voltage is being applied in the electrodes, the food material or the liquid food which has to be heated is passing through in between the two electrodes. So, that is where it is told in contact with the electrodes. Ohmic heating is very often used in pasteurization, sterilization of fluid food products, pumpable fluids, in which the contact with the electrodes is not a serious problem, resulting in an excellent quality. So, sometimes what happens, certain food material will enhance the corrosion in the electrodes. So, if that is the case, some of the corroded materials may also get into the food. So, it is very much employable and gives the excellent quality when such problem is not arising. Such problem in the sense there should not be any corrosion in the electrodes due to the liquid food product to be heated. So, the electro process used for pasteurization of milk had been named as a electropure. The pasteurization of milk using ohmic heating technique is called electropure, and after ohmic heating got well established, So, there was a drop in using the technology commercially due to higher electricity prices and electrolysis related effects. So, electrolysis in the sense, one is the electrodes get corroded and it comes into the food, and sometimes what happens due to electrical heating, some of the components of the food material also get denatured, because when you are using the food in the presence of electrodes, there may be a corrosion in the electrodes and those corroded material can also get into food, or otherwise due to electrolytic reaction some of the food fragments also get denatured, right. So, these effects are unwanted, and process regulation, there were no process regulations employed for the ohmic heating, and there were certain technical limitations were also there. So, due to these reasons, once it picked up, then there were no commercial plants, there were no commercial technology, right. Then after that, with the solid state power supply technology, it is now possible to use ohmic heating in pulse mode, pulsed ohmic heating, to economically control electrolytic effects to innoxious level. And ohmic heating systems are now better engineered and more sophisticated, far less expensive than their preceders to produce ohmic heating equipment. So, there was a certain dip in between, but again it got picked up due to technology advancement. So, now we are going to see the lab scale system which is designed for ohmic heating. So, the first one is here, it is a principal system. So, this is the principle with which the ohmic heating works. So, here is your the processing system. So, fluid in is this one and fluid out is this one. So, AC supplies the voltage. So, the current is flowing through the liquid material directly. So, here is the lab scale system developed. So, I have given the reference in the last slide. So, where you can find these lab scale as well as pilot scale system. And in the lab scale system, you have a AC supply to give electrical energy to the system, and there is a variac, so which controls the desired voltage, and it is given to the power controller. So, here you have a voltage as well as the current measurement units. So, this is called your ohmic heating unit, heater tester unit. So, which includes the sample cell as well as the electrodes. So, this is a static ohmic heater box. So, here you have your fluid food and here you have electrodes as well. And we have a temperature measurement system, and if you have a fluid food, then you may be having the flow rate control as well, right. And to record all the data, temperature or flow, and you will have a microcomputer system as well. And so, this is insulated completely using the polypropylene box, and two type K coated titanium plate electrodes are used. The electrodes used here is titanium plate electrodes, and the frequency applied is 50 hertz current and 240 voltage, 240 volt voltage, and K type thermocouple with the PTFE coating is used to measure the temperature within the cell, which is nothing but a ohmic cell. So, PTFE is nothing but a polytetrafluoroethylene, polytetrafluoroethylene. So, these coatings are used in order to avoid the corrosion when it is directly facing the fluid food products. So, this is the pilot scale system. So, if you see here, this is a feed pump. So, mostly positive displacement pump. So, this is your ohmic heater column. So, you have 3 different sections. So, this is the Hall effect sensor. Hall effect sensor is just to measure the voltage. So, as I told already, there are a lot of technology improvement. So, even now they were using RFID system to measure the voltage. So, earlier it was recorded using the Hall effect sensor. Hall effect is nothing but, so when the magnetic field is applied perpendicular to the current, then you can measure the voltage across the section through which the current is flowing. So, now they are using RFID system, but when you use the sensor depends upon that you supposed to design the column as well. In Hall effect sensor, this may be a metal column, for example a SS metal can be used, but if you use the RFID system, there may be a frequency interferences between the stainless steel material and RFID system. So, in that case you may be using the glass system, right. So, this is up to the choice of the production unit, whatever you wanted to use you can use, but it should be designed carefully, right. Here you have a 3 heater ohmic column, then after that it goes to product holding tube. So, what we have seen in previous lectures, how the inline pasteurization or sterilization is conducted. We have a heater, we have a holding tube, and after that cooling section. So, here the heater column is nothing but a ohmic heater column, except that then everything else is same. So, you have a product holding tubes here, and here you have a cooling section. So, where your cooling water is used to cool the product. Then after that it goes for aseptic storage or packaging. So, heating column, holding and cooling tubes, and 3 electrodes housing, each containing cantilever electrode. The electrode here is cantilever electrode. The electrode housings are connected with spacer tubes, which gives 2 heating section. So, if you see here, then you will understand better. So, this is the thing. So, there are 3 heating sections. So, this is nothing but your electrode housing. So, here you have the electrode. So, electrode. So, here this spacer tube gives the 2 different heating sections, and the product is introduced into the system via twin piston PLC metering pump. So, as I said earlier, so this pump is of your choice. So, based on your fluid product what you use for ohmic heating, the pump is designed to allow the fluid particles to pass through with minimal damages and is adapted for high viscous and particulate foods. So, as we told already, the mainly ohmic heating is employed for high viscous and particulate foods. So, we need to design pump accordingly, which should allow fluid food particles to pass through with minimal damage, and the product was collected at the exit of the cooling section and returned by means of a flexible tube to the pump. And due to increased electrical conductivity of the products as heat increases, the connecting tube increases in length throughout the system to maintain same electrical impedance. So, you must be wondering, so why you have a the connecting tubes here, right. So, that is the purpose here. So, due to increased electrical conductivity of the products as heat increases, the connecting tube also increases in length throughout the system to maintain the electrical impedance same. So, in all sections the electrical impedance should be same. So, this is simple same thing what we have seen here. So, as I told earlier, so this system can be, this system in the sense ohmic heater column can be designed based on one's own choice. So, which housing you wanted to provide, which sensors you wanted to provide, or which kind of heating column you wanted to provide, it is based on our choice. So, I have given 2 different systems. One is this system where you have a heating sections here and you have a electrode in between, and electrode housing is nothing but this whole setup, right. And here another one you can see. So, this is vertical, all right. So, this is to take care of the upward flow. So, this is slanting sections. Okay. So, here you will find 2 electrodes here, and also here you have a mixture rod mixture rod will give the agitation to give the proper mixing for the fluid. So, this is the product flow, alright. So, here you will get it at the exit. So, other than that there is not much difference between them. So, you can have a mixture rod or you cannot have. So, it depends upon the requirement of the industry or requirement based on the fluid food products. The applications, the ohmic heating system can be adapted to aseptic food processing lines. So, we have already told pumpable fluids, and temperature required for UHT processing can also be achieved using ohmic heating. Ability to heat materials rapidly. So, this we have just seen in the advantages, and uniformly leading to a less aggressive thermal treatment. So, my temperature is not that high, and it can pasteurize the proteinous foods such as liquid egg, whey without coagulation. So, since my temperature is not increasing that much, there is no aggressive thermal treatment. So, it can pasteurize proteinous products which may be difficult using the conventional thermal processing technologies. So, especially whey without coagulation, and degradation of proteins and fouling in the equipment surfaces during ohmic heating is less compared to the conventional heating method. So, here due to degradation of protein, so it will not form a layer near the electrode. So, if it forms the layer near the electrodes, then may be a overheating near the electrodes, because the formed layers, for example, so you have a electrode here. So, if my fluid particle forms the fouling or scaling near the electrode, so then here it will get heated fast, get heated higher rate, right. Why it is higher rate? Because this may not be able to move. So, in that case, so it gets heated at higher rate. So, this may be the problem. Degradation of proteins and fouling in the equipment surface during ohmic heating is less compared to conventional heating method. So, the overheating near the heating surface is less in ohmic heating compared to conventional heating method. There is no need for mixing of fluids, fluid foods for homogeneous heating, which is important for food sensitive to mechanical damage. So, normally whatever the conventional thermal processing methods available, so there if I use the agitation, so you might have seen also, right, there are a couple of lectures we have also specifically given weightage to the agitation principle, right. So, if I do the agitation, then my heat transfer will be enhanced. So, but in the food side, that may be a disadvantage, because there are some foods which are sensitive to mechanical damage. So, to avoid agitation, I can also employ ohmic heating, because it gives me homogeneous heating without any agitation, because it works under the principle of volumetric heating phenomena. Energy conversion efficiencies are very high, of course, and small equipment footprints and are generally quiet, and it will not make any noise due to thermal stresses, and instant on off is possible. If you have seen somewhere in previous lectures the come up time, right. So, once I switch on, so how long it takes to heat the container and heat the food. So, that can be avoided here, because it is a instant on off, and also system can be shut down instantly if any problem occurs, and accurate temperature control is possible using proper process control system. And the issues wise, we need to take care of proper electrical insulation and accurate process control system. So, when I was mentioning here itself, I told accurate temperature control is possible only when, so if you use accurate process control system, and well trained personnel are needed, and toxicological and mutagenic substances production. So, this is the area which is not much explored. As I already told, so there may be a possibility for a electrolysis as well as the corrosion of electrodes, and which is directly, because we are heating the food products directly using the electrodes. So, there may be a chance for toxicological as well as mutagenic substance which goes into food. And precise information on assurance of its lethality in various kinds of food is also the area which needs to be explored in terms of ohmic heating, because the property of the food extensively affects the ohmic heating. We will see in subsequent slides. So, why it is so, and installation costs are very high, as we told in all non-conventional thermal processing technologies, but processing cost is almost comparable with any of the thermal processing technology. And presence of non-conductive parts or some components such as fat globules, right. So, if it is there, so its electrical conductivity is very less. So, if your food product contains the fat globules, what happens is, so that particular place will not be heated much. So, if it is not heated much, there may be a contamination, local contamination. So, this is the serious issue in ohmic heating. So, presence of non-conductive parts, and temperature increases highly rapid and uncontrollable, it creates the possibility of runaway heating. So, this is also important because the time versus electrical conductivity, that relation is almost a linear relationship, B T1 plus C. So, B and C are constants. So, almost the temperature increases linearly with the electrical conductivity. So, in that case, if it increases the rapidly, so it becomes uncontrollable, then there is a possibility for runaway heating. So, that is also one of the issue in ohmic heating. And development of adequate safety and quality assurance protocols in order to obtain an approved filing of the process with FDA for all possible food materials. So, this is very much important. It is not only true for ohmic heating, for any process, for any food processing technology. So, we need to take care of the safety and quality assurance protocols because it is of public health significance. So, this is true for almost all non-thermal or thermal technologies, so which are going to be applied commercially. And what are all the main process control parameters to be considered in ohmic heating is the voltage gradient, what we apply, the frequency and the temperature range, and the electrical conductivity differences and electrode type, right. So, this is on the electrical system parameters, and voltage, current and power applied across the electrode, and the current density is nothing but a ampere per meter square. So, which is nothing but a current upon area, right. So, this is another critical parameter which is to be considered in the ohmic heating. And flow properties in the pumping system, because it is used for pumpable foods. So, we need to take care of the flow properties, because for example, the mass flow rate is a main critical factor, and which type of food material we use. So, one of the lectures I mentioned about Newtonian and non-Newtonian, and also which type of flow we are encountering, for example, laminar or turbulent. So, that also matters, right. So, all these to be taken care. And the fruit and vegetable products, for example, juices, purees and pulps are also successfully ohmically heated. Their high heating rates, which are depend on the voltage gradient applied, provide the opportunity to blanch or pasteurize them quickly and uniformly compared to conventional thermal technologies. So, one of the main parameter how we have solid conventional thermal processing of solid foods, thermal conductivity was the main parameter, and in terms of liquid food product, the heat transfer coefficient. So, here in ohmic heating, the electrical conductivity is the critical factor. So, it depends upon the ionic breakup and microstructure of the food material undergoing heating. So, if you remember, the current which is flowing through the food is nothing but a flow of electrons, right. So, how much it depends upon the ionic breakup as well as the microstructure of the food material which is undergoing heating. For example, if I have a food product which has a sugar as well as the fat globules, may influence the electrical conductivity of the sample depending upon their electrolytic characteristics. For example, for sugar and fat globules, so my electrolytic characteristics may be different. So, based on that only it shows up the electrical conductivity when voltage is applied between the electrodes. In fruit juices, the main solute component is the sugar, which is having a non-electrolytic behavior, but the acidity of the juices enhanced their electrical conductivity. For example, sugar has non-electrolytic behavior, but that will be compensated if your juice is having acidity nature, because the acidity nature enhance the electrical conductivity. So, basically it is an example. So, you cannot determine or you cannot generalize the food materials by saying wherever the sugar component is there, so it will have non-electrolytic behavior. So, it also depends upon the other components of the food material. For example, if the sugar and acidity content both are there, so the non-electrolytic behavior of the sugar can be compensated using the acidity of the fruit juice. Electrical conductivities of fruit and vegetable juices increased linearly by decreasing the insoluble solid contents. So, if there are high amount of insoluble solid contents, then your electrical conductivity may be reduced. So, decrease in electrical conductivities occurs after bubbling starts. Actually, this bubbling is a phenomena when you have a water. So, there may be a bubbling phenomena. So, we are going to see in next slide. So, if that is a bubbling occurs, then there may be a decrease in electrical conductivity. So, this is the table which talks about the different fluid food and the temperature ranges and the voltage gradient applied across the electrode and the concentration ranges in the food material and electrical conductivity. So, this you can get in the reference itself. So, for example, I will just would like to highlight few. Orange juice, the temperature range is 25 to 80 and 30 to 60. And the voltage gradient applied is 42.42 voltage per cm, and if it is a temperature range is between 30 to 60, then you are supposed to apply 20 to 60 voltage per centimeter, and also it depends upon the mass fraction. So, here you have a 0 to 21% solid content, here 0.2 to 0.6 mass fraction. And also the electrical conductivity is high in terms of when you apply 42.42 volts per cm, it contains 21% solids, but if you go for 0.2 to 0.6 mass fraction, so your electrical conductivity is decreased 0.15 to 1.15 Siemens per meter. So, you can see the such kind of tables in the reference material given. So, the next important parameter is the temperature. We have seen about the electrical conductivity, because the ohmic heating to be applied, the food material should have electrical conductivity. So, that is what we have seen. And now the second one is the temperature. The change in the temperature during ohmic heating is very fast, we have just seen, and could result in runaway heating. And in continuous system, the power applied during heating can be adjusted by using feedback or feed forward control. This is very much important, because if it heats rapidly, then there may be a runaway heating. Measurements of temperature, mass flow rate and specific heat capacity. As I told in previous slide, the temperature, mass flow rate as well as specific heat capacity changes during ohmic heating should be measured then and there to have a precise control of the system. In batch systems, the temperature measurements taken from the different points of the food help the observation of the maximum temperature limit and necessitate the on of the power supply. So, in the batch system, we employ the thermocouple and get the temperature measurements then and there using the digital display. So, if we feel it goes to the maximum temperature limit, then we can switch off the power supply. And the electrical insulation of the temperature probe used is very much important in avoiding undesired signal disturbance in the measurement system. So, what we are using is electrical energy to heat the fluid. So, in such case the temperature probe what we use also should be insulated properly, otherwise it will have undesired signal disturbance, because this is also electrical, that is also electrical. So, signal disturbance would be there. So, the insulation of the temperature probe whatever we use for the temperature measurement should be insulated properly. And since the ohmic heating takes place in seconds for high acidity fluid foods, the sensitivity of the temperature probes should be high and the response time should be low enough. So, this is also another important criteria when we use the thermocouples to measure the temperature inside the food material, because the probe should be high, that is nothing but sensitivity. Sensitivity in the sense, so how fast it measures the temperature and give the digital display, right. And also the response, for example, if I keep the thermocouple, how fast it responds to the temperature difference and how fast I will be able to get that data recorded. These two are important parameters, and specially coated T-type thermocouples have been used in several studies for the purpose of temperature measurements during ohmic heating. So, the T-type thermocouple. So, this the same thermocouple we have seen to be used in validation purpose also, right. So, validation temperature distribution test. So, there also we use the T-type thermocouple. And one more the picking up the recent technology is non-invasive. Non-invasive in the sense, since both are electrical systems, the thermocouple whatever thermocouple we get in terms of digital signals, right. So, since both are involving the electrical signals, there may be a disturbance. So, due to which the non-invasive temperature mapping techniques were developed. So, one such is magnetic resonance imaging, which allows the production of 2 or 3 dimensional temperature maps of ohmically heated food materials without disconnecting the electrical heating power, and also allows the estimation of the fluid particulate heat transfer coefficient for food mixtures in the ohmic heating during holding period. So, this is what they do is they employ the magnetic particle, so which is nothing but a tracer particles, right. So, this is used as a tracer particle to measure the temperature inside the holding tube. So, this also will be sent along with the fluid, and it is further used for temperature measurements. So, this helps me as an alternative to the normal conventional thermocouple temperature measurement system. And another important critical factors is electrodes and electrochemical reactions. The contamination of food with metal ions migrated from the electrodes and the resulting electrochemical reaction products. So, this is the critical thing when we use the ohmic heating. So, the contamination of the food by the metal ions migrated from the electrodes. So, this contamination could be either toxic, which is nothing but a carcinogenic, and bring undesired taste or color in the processed food. That is another problem why most of the consumers will not prefer electrically heated food. The better electrode materials are by operation at high frequencies. So, we can avoid such electrochemical reactions in the electrodes, and use of surface material with lower corrosion tendency. So, that is nothing but titanium or gold. So, if you see in our pilot scale, so here we use type K coated titanium plate electrodes. So, that is to avoid the corrosion or electrochemical reactions. So, normally the lower corrosion tendency materials, which is nothing but a titanium or gold, is used, or the coating of the existing surfaces with the less corroding materials may be also option, the platinized titanium. So, this also can be used, and pulsed ohmic heating is another option for minimizing the electrochemical reactions and the formation of gas bubbles during ohmic heating. So, the formation of gas bubbles as well as the minimizing electrochemical reactions can be taken care by the pulsed ohmic heating. So, pulsed ohmic heating, I suppose to use one more pulse generator to create the current. So, the gas bubbles, so we have seen, right. So, if there is a bubbling there may be a reduction in the electrical conductivity, right. So, these gas bubbles, where from they are coming, right. So, are the results of either water boiling due to localized high current densities, or the byproducts of various oxidation and reduction reactions, for example H2 or O2 gas. So, due to which also there may be a bubble formation, or naturally the water boiling also creates the bubble formation. So, whatever way, but it is undesired in the ohmic heating. If the air is occluded in the sample, air bubbles expanded with the temperature with the pressure remaining constant. So, this is also problem. So, it starts growing and it collapses with each other. So, that is also a problem, and the electrolytic reactions were not evident with specifically coated electrodes in the use of high frequency power. So, this we have seen here as well, either I need to use better electrode materials or by operation at higher frequencies. So, pH is another important factor in the electrode corrosion and electrolytic reaction. So, this is very much important, pH and temperature, which also enhance the electrode corrosion and electrolytic reactions. So, this is just to give two examples. So, we cannot generalize anything here. So, that is what I wanted to tell you this. The pulsed ohmic heating at higher frequencies, that is what we have told, right. So, if we take care of the higher frequency, then the electrode reactions may be avoided. So, pulsed ohmic heating at higher frequencies and shorter pulse widths yielded the lowest rates of electrochemical reactions for stainless steel electrodes, but pulsed ohmic heating at lower frequency and longer pulse width was more effective in suppressing the electrochemical reactions of titanium as well as platinized titanium electrodes. So, we cannot generalize, but the optimum value should be found out. Optimum values should be found out based on the food material and electrodes used. Based on food material and electrode. Okay, so, we cannot generalize. So, in general, that is the case, means the better electrode materials at higher frequencies will avoid the electrochemical reactions, but certain food materials it may not be true as well, right. There are exceptional cases always. And the food properties which are also very much important when we apply the ohmic heating, the acidity. So, we have already seen acidity increases the electrical conductivity, the composition of the food material. For example, we have told if my fluid food has the fat globules, so then it shows the non-electric behavior. So, because of that there may be a cold spot in the food material. So, because which cannot conduct the electricity. So, in that case it may not get heated to the optimum level. So, there may be a cold spot in the food material. And rheological properties, for example, I have told you, right, the Newtonian and non-Newtonian food. So, the non-Newtonian food, there are two important criteria we need to take care. One is flow consistency, another one is flow behavior. So, in one of the lectures also we have told, right, most of the food materials are behaving with the non-Newtonian fluid behavior. So, these two important parameters we supposed to consider. So, that is where the rheological properties of the food is very much important for the ohmic heating. And total solid content, one of the point we have seen is if we increase the solid content, there may be a reduction in the electrical conductivity. Right, and viscosity of the liquid food, this is also related to the rheological property behavior. If the fluid is in the form of solid liquid mixture, so we need to take care of the particle dimension, because it is a pumpable fluid. I need to employ the pump also based on the characteristics of the fluid product what we use, and the orientation and the density of the solids in the liquid mixture, and the electrical conductivity ratios of the solid and liquid. So, this is very much important, because when you have a liquid as well as the solid particle. In the thermal processing technology, we might have told right, the heat transfer coefficient and the thermal conductivity of the solid material should be far matched, otherwise the convection may be very fast and conduction will be very slow, then in such case you will have the overheating at the surfaces. The same thing here. So, when we use the solid particulates in the liquid, the electrical conductivity ratios between the solid and liquid is also very much important when we employ ohmic heating. The difference between the electrical conductivity and specific heats of the solid and liquid phases in the mixture will extensively affect the temperature distribution in the ohmic heating column. So, this is the difference between the electrical conductivity and specific heats of the solid and liquid phases. So, this we have seen in the previous slide itself. So, how it affects the ohmic heating. The physical and electrical properties of the food should be known and taken into account in the design procedure. So, this is very much important, the electrical properties as well as the physical properties, which is nothing but a density, dimension, etc., also to be taken care when we use the design procedure. So, then there comes the flow properties. So, flow properties in the sense I have already mentioned, right. So, then we supposed to know which type of flow it is encountering, whether laminar or transition or turbulent, and also important thing is the Newtonian and non-Newtonian. Right. So, when we use such a cases, I have also mentioned. So, for example, you have a electrode here. So, based on the flow consistency index, so what may so happen is the fluid layer which is next to the electrodes, right, so will not move faster. So, in that case, so it may get heated at a higher rate and it will cause the overcooking or over processing. So, this can be avoided if we know the flow properties inside the ohmic heating column well. So, one such technique is, this is nothing but a PIV technique. So, which is used to see the local velocity variations inside the cell, right. So, this technique uses image processing to get to know the velocity. So, this is normal computer system. So, this is CCD camera, so which has higher pixel rate as well as the per second how many shots it can take, also it is very much higher. So, this is a high end camera. So, this is the computer system. So, this is the synchronizer. So, this is laser. So, this is lens. So, this is the laser light. This is the test cell, which is having proper height, thickness and width. And this is a flow controller. So, this is pump. So, this is a tank. Okay. So, from here the fluid is pumped and using the flow controller it goes to test cell, then it comes back. So, here what we are using is, we are using the laser light. So, this test cell also has carrier particles. So, as I told earlier, so this is my fluid. So, I also employ the tracer particles in the fluid food material. So, what happens is, this laser light so follows the tracer particle, so which is called a tracer particles. So, this is also moves in par with the fluid velocity, right. So, this laser light targets the tracer particle. So, this is taken as a image using the CCD camera, then it is image processed and we will get to know what is the, this is the power input. Okay. So, what happens is, so I employ the laser light into the test cell. The test cell also contains the tracer particle. So, the tracer particle movement will be captured by the camera, then after that I image process and get to know the velocity of the tracer particle. So, velocity of the tracer particle is nothing but a liquid velocity. So, if I know localized liquid velocity, then I may get an idea about the distribution of the temperature inside the test cell, right. So, for example, how it can be modeled is, so we already know the continuity equation in any system. So, this is grad dot rho v, right. So, this is a density, this is the fluid density which is in kg per meter cube. So, this is the time with respect to time. So, this is nothing but density into velocity, v is nothing but a velocity vector. So, if you write the same principle using the ohmic heating, so this is nothing but dou rho c upon dou t. So, this is nothing but a current density here, right. So, plus grad sigma grad v. So, this is sigma is nothing but electrical conductivity, so which is in Siemens per meter, and this V is nothing but a electrical potential, so which is nothing but a voltage here, right. So, this is in ampere per meter cube. So, if we combine the ohmic heating principle with the continuity equation, then this is the equation which is equivalent to 0. So, at steady state where there is no time dependency, then I can say grad sigma grad v which is equivalent to 0. So, from this I can calculate the heat generation rate, so which is nothing but a volumetric heat generation, rate, so which is equivalent to grad v square into sigma. So, this further u dot is taken into account. So, when we use the normal energy balance equation. So, normal energy balance equation for solid food k grad T which is equivalent to rho Cp dou T upon T. So, here you will take the heat generation as well. This is a heat generation rate. Okay. So, to get to know this for liquid food, so we supposed to get the localized velocity. So, this will give me how the temperature is, because in convection system, so your temperature alters your velocity and velocity alters your temperature. So, this would give me localized velocity, from that I can model the system better. So, normal thermal processing will have only these components, right, but here you have a volumetric heat generation. So, that can be related to the ohmic heating principle using this equation. Okay. So, you can refer these further references and additional resources. So, I have taken the tables from this particular reference. So, you may would like to refer more for further in-depth knowledge about the electrical conductivity and how much voltage difference to be applied between the electrodes based on the food products. Thank you.